Last week, we were introduced to the notation of algorithms using the GCD example. We also saw informally some Python code which we could understand, but we have not actually been introduced to formal Python syntax. So let's start with some real Python this time. A typical Python program would be written like this. We have a bunch of function definitions followed by a bunch of statements to be executed. So remember that we said Python is typically interpreted. So an interpreter is a program which will read Python code and execute it from top to bottom. So the interpreter always starts at the beginning of your Python code and reads from top to bottom. Now a function definition is a kind of statement, but it doesn't actually result in anything happening. The Python interpreter merely digests the function. It kind of remembers the function definition so that later on, if an actual statement refers to this function, it knows what to do. So in this kind of organization, the execution would actually start with the statement which is called statement 1. So first you will digest k functions and then start executing 1, 2, 3, 4 up to statement n. Now there's no reason to do this. So Python actually allows you to freely mix function definitions and statements. And in fact, function definitions are also statements of a kind. It's just they don't result in something immediately happening, but rather in the function being remembered. But one of the things that Python would insist is that if a function is used in a statement that has to be executed, that function should have been defined already. Either it must be a built-in function or its definition must be provided. So if we use this kind of jumbled up order, we have to be careful that functions are defined before they are used. Also, jumbling up the order of statements and function definitions in this way makes it much harder to read the program and understand what it's doing. So though it's not required by Python as such, it is strongly recommended that all function definitions should be put at the top of the program and all the statements that form the main part of the code should follow later. So what is a statement? Well, the most basic statement in Python is to assign a value to a name. So we see examples and we have seen examples, and here are some examples. So in the first statement, I is a name and it's assigned a value 5. In the second statement, j is a different name and it's assigned an expression 2 times I. So in this expression, the value of I will be substituted for the expression I here. So if I has not already been assigned a value before, Python would not know what to substitute for I and it would be flagged as an error. So when you use a name on the right hand side as part of an expression, you must make sure that it already has a valid value. And as we saw, you can also have statements which merely update a value. So when we say j equal to j plus 5, it's not a mathematical statement that the value of j is equal to the value of j plus 5, but rather that the old value of j, which is on the right hand side, is updated by adding 5 to it, and then it gets replaced as a new value of j. So this is an assignment statement. This equality assigns the value computed from the right hand side given the current values of all the names to the name given on the left hand side, and the same name can appear on both sides. So the left hand side is a name, the right hand side in general is an expression, and in the expression you can do things which are legal given the types of values in the expression. So values have types. If you have numbers, you can perform arithmetic operations. If you have some other things, you can perform other operations. So what operations are allowed depend on the values, and this is given technically the name type. So when we say type of value, it's really specifying what kinds of operations are legally available on that class of values. So the most basic type of value that one can think of are numbers. Now in Python and in most programming languages, numbers come in two distinct flavors, as you could call them: integers and numbers which have fractional parts. So in Python, these two types are called int and float. So int refers to numbers which have no decimal part, which have no fractional part. So these are whole numbers, they could be negative. So these are some examples of values of type int. On the other hand, if we have fractional parts, then these are values of type float. So normally in mathematics, we can think of integers as being a special class of, say, real numbers. So real numbers are arbitrary numbers with fractional parts. Integers are those real numbers which have no fractional part. But in a programming language, there is a real distinction between these two. And that is because of the way that these numbers are stored. So when Python has to remember values, it has to represent this value in some internal form, and this has to take a finite amount of space. So if you're writing down, say, a manual addition sum, you will write them down on a sheet of paper, and depending on the sheet of paper and the size of your handwriting, there is a physical limit to how large a number you can add on that given sheet of paper. So in the same way, any programming language will fix in advance some size of how many digits it uses to store numbers. And in particular, as you know, almost all programming languages will internally use a binary representation. So we can assume that every number, whether an integer or a real number, is stored as a finite sequence of zeros and ones which represents its value. Now, if this happens to be an integer, you can just treat that binary sequence as a binary number, as you would have learnt in school. So the digits represent powers of 2. Usually there will be one extra binary digit, 0 or 1, to indicate whether it's plus or minus, and there may be other more efficient ways of representing negative numbers. But in particular, you can assume that integers are basically binary numbers. So they're just written as integers in binary notation. Now when we come to non-integers, then we have two issues. One is we have to remember the value, which is the number of digits which make up the fractional part. And then we have to remember the scale. So think of a number in scientific notation, right? So you normally have two parts when we use things in physics and chemistry, for instance. We have the value itself, that is, what are the components of the value, and we have how we must shift it with respect to the decimal point. So this says move the decimal point 24 digits to the right. So this first part is called the mantissa, right? And this is called the exponent. So when we have a number in memory, if it is an int, then the entire string is just considered to be one value. Whereas if we have block of digits which represents a float, okay, then we have some part of it which is the mantissa and the other part which is the exponent. So the same sequence of binary digits, if we think of it as an int, has a different value, and if we think of it as a float, has a different value. So why float, you might ask? So float is an old term from computer science called floating point. It refers to the fact that this decimal point is not fixed. So an integer can be thought of as a fixed decimal point at the end of the integer. A floating point number is really a number where the decimal point can vary, and how much it varies depends on the exponent. So there are basically fundamental differences in the way you represent integers and floating point numbers inside a computer, and therefore one has to be careful to distinguish between the two. So what can we do with numbers? Well, we have the normal arithmetic operations, plus, minus, multiplication, which has a symbol star, not an X, and division, which has a symbol slash. Now notice that for the first three operations, it's very clear. If I have two ints and I multiply them or add them or subtract them, I get an int. If I have two floats, I will get a float. Division, on the other hand, will always produce a float. So if I say 7 and divide it by 2, for instance, where both are ints, I will get an answer 3.5. Now, in general, Python will allow you to mix ints and floats. So I can write 8 plus 2.6, even though the left is an int and the right is a float, and it will correctly give me 10.6. So in that sense, Python respects the fact that floats are a generalized form of int. So we can always think of an int as being a float with a 0.0 at the end. So we can sort of upgrade an int to a float, if you want to think of it that way, and incorporate it in an expression. But division always produces floats. So 7 divided by 3.5 is an example of a mixed expression where I have an int and a float, and this division results in 2.0. And 7 by 2 results in 3.5. Now there are some operations where we want to preserve the integer nature of the operands. We have seen one repeatedly in GCD, which is the modulus operator, the remainder operator. But the corresponding operator that goes with remainder is the quotient operator. So if I use a double slash, it gives me the quotient. So 9 double slash 5 says how many times does 5 go into 9 exactly without a fraction, and that is 1, because 5 times 1 is 5 and 5 times 2 is 10, which is bigger than 9. And the remainder is 4, so 9% 5 will be 4. Another operation which is quite natural and common is to raise one number to another number, and this is denoted by double star. So 3 double star 4 is what we would write normally as 3 to the power 4 is 3 times 3 times 3 times 3 4 times, right? And this is 81. Now there are more advanced functions like log, square root, sine and all, which are also built into Python, but these are not loaded by default. If you start the Python interpreter, you have to include these explicitly. So remember we said that we can include functions from a file that we write using this import statement. So there is a built-in set of functions for mathematical things which is called math. So we must add from math import star. This can be done even within a Python program. It doesn't have to be done only at the interpreter. So when we write a Python program where we would like to use log, square root and sine and such like, then we should add the line from math import star before we use these functions. So we have seen three concepts: names, which are what we use to remember values; values, which are the actual quantities which we assign to names; and we said that there's a notion of a type, right? So a type determines what operations are legal given the values that we have. So the main difference between Python and other languages is that names themselves don't have any inherent type. I don't say in advance that the name I is an integer or the name X is a float. Names have only the type that they are currently assigned to by a value that they have. Right? So the type of a name is not fixed. In a language like C or C++ or Java, we announce our names in advance. We declare them and say in advance what type they have. So if we see an I in an expression, we know in advance that this I was declared to be of type int and this X was declared to be of type float and so on. Now in Python, this is not the case. So let us illustrate this with an example. So the main feature of Python is that a name can be assigned values of different types as the program evolves. So if we start with an assignment I equal to 5, since 5 is an int, I has the type int. Now, if we take an expression which produces an int, such as 7 times 1, I remains an int. Now, if we divide the value of I by 3, so at this point, if we had followed this sequence, I is 7, right? So 7 by 3 would be 2.33, and this would be a float. So therefore, because the operation results in a float, at this point, j is assigned a value of type float. Now, if we continue and at some later stage, we take I and assign it the value 2 times j. Since j was a float, I now becomes a float. In the interpreter, there's a useful function called type. So if you type the word type and put an expression, either a name or an expression in the bracket, it will tell you actually the type of the expression. Now, although Python allows this feature of changing the type of value assigned to a name as the program evolves, this is not something that is recommended, because if you see an I and sometimes it's a float and sometimes it's an int, it is only confusing for you as a programmer and for the person trying to understand your code. So in the same way that we said before that we would like to organize our Python code so that we define all functions before we execute statements, it is a good idea to fix in advance, in your mind at least, what different names stand for and stick to a consistent way of using these either as ints or as floats. So let's execute some code and check that what we have been saying actually happens. So supposing we start the Python interpreter and we say I is equal to 5. Then if we use this command type I, it tells us the type of I. So it returns it in a form which is not exactly transparent, but it says that I is of class int. So you see the word int. If I say j is equal to 7.5 and I ask for the type of j, then it will say that j is of class float. So the names int and float are used internally to signify the types of these expressions. Now if I say I is equal to 2 times j, as we suggested, I has a value 15.0 because j was a float, and therefore the multiplication resulted in a float. And indeed, if we ask for the type of I at this point, it says that I is now a float. So the point to keep in mind is that the names themselves don't have fixed types. They are not assigned types in advance. It depends on the value that is currently stored in that name according to the last expression that was assigned. Another important class of values that we use implicitly in all our functions are Boolean values, which designate truth or falseness. So there are two constants or two basic values of this type, which in Python are called true with a capital T and false with a capital F. Right? So true is a value which denotes something is true. So when we remember, we wrote conditions like if something happens, if x is equal to y, do something, or if x mod 7 is equal to something, do something in our GCD function. So the output of such an expression where we compare something to another expression, compare an expression on the left to an expression on the right, is to determine whether this comparison succeeds or fails. When it succeeds, it is true. When it fails, it is false. So these are implicitly used to control the execution of our program. So we need to have a way of recording these values and manipulating them. So the basic values are true and false. And typically there are three functions which operate on these values. So not negates the value. So true is the opposite of false. So not applied to true will give us false. Not applied to false will give us true. And follows the usual English meaning of and. So when we say that something is true and something else is true, we mean that exactly both of them are true. So x and y, two values of Boolean type, the expression x and y will be true provided at the moment x has a value true and y also has a value true. If either of them is not true, then the output x and y is false. Or again has an English meaning, but the meaning in computer science and logic is slightly different from what we mean. So normally when we say or, we mean one or the other. So you might say either I will wake up in time or I will miss my bus. So what you mean is that one of these two will happen. It's unlikely that you mean that you will wake up in time and you will miss your bus. Right? So when we use or in English, we usually mean either the first thing will happen or the second thing will happen, but not both. But in computer science and logic, or is a so-called inclusive or, not exclusive. It's not exclusively one will happen or the other, but inclusive. Both may happen. So x or y is true if at least one is true. So one of them must be true, but it's also possible that both of them are true. So the most frequent way in which we generate Boolean values is through comparisons. So we have already seen two of these. So we have seen equal to. So this is the actual equality of mathematics, not the single equal to, which is assignment. So x equal to y checks whether the value x is actually the same as the value y, and if so, it returns the value true, otherwise it returns false. And the corresponding inequality operator is an exclamation mark followed. So this is not equal to. Exclamation equal to is a symbol for not equal to, and this is the usual mathematical equal to. And then of course you have, for values which can be compared as smaller or larger, you have less than, greater than. This is less than, equal to, and this is greater than, equal to. So we have these six logical comparison operators, arithmetic comparison operators, which yield a logical value true or false. And the usual thing we will do is combine these. So we might want to say that check if the remainder when divided by n is 0, provided n is 0, not 0. So if you say n is greater than 0 and this, it will require n to be number bigger than 0 and the remainder m divided by n to be equal to 0. So this says m is a multiple of n and n is not 0. And we can take an expression of this kind, a kind of comparison which yields, as we said, a Boolean value, and take this Boolean value and assign it to a name. So we can say that n is a divisor of m if the remainder of m divided by n is 0. And we can say that the fact that it's a divisor is true provided this happens. So divisor is now of type Bool, right? And it has a value true or false depending on whether or not n divides n evenly. So let's look at an example of how we would use Boolean values. So let's get back to the divides example. So in mathematics, we write m divides n to say that m is a divisor of n. Okay? So this means that m times k is equal to n for some k. So m divides n if the remainder of n divided by m is 0. So if so, you return true, else you return false. Right? So this is a very simple function. It takes two arguments and checks if the first argument divides the second argument. Now what we can do is define another function called even, whose value is derived from here. So we check whether 2 is a divisor of this number. So we check whether 2 divides n. If 2 divides n, then n is even, we return true. If 2 does not divide n is odd, we return false. So similarly, we could say define odd n as the negation of the previous case. So if 2 divides n, then n is not odd. So you take the answer about whether 2 divides n or not and reverse it to get the answer odd. So if 2 divides n, you negate it and say odd is false. If 2 does not divide n, you get false back, you negate it and say odd is true. So we just wanted to emphasize that Boolean values can be computed, assigned, passed around just like numerical values are. So to summarize, what we have seen is that the basic type of statement is to assign a name to a value. Values have types and these determine what operations are allowed. So we can use, for instance, arithmetic operations on numeric types. We can use logical operations like and, or, and not on Boolean types. But the important difference between Python and traditional languages where we declare names in advance is that Python does not fix types for names. So we can't say that I has a type int forever. I will have a type depending on what it's assigned. So a name inherits the type from its currently assigned value, and its type can change as the program evolves depending on what values have been assigned. So what we have seen in this particular lecture are 3 basic types: int, float, and bool. As we go along this week, we will see more types with interesting structures and interesting operations defined on them.